So if you're a researcher, you know this feeling. You've got your results, you're staring at the data, but is it real? Is this a genuine discovery, or are you just seeing a ghost in the machine? Today, we are diving deep into the two major ways scientists try to answer that exact question.
All right, here's how we're going to break it down. First, we'll get right into the fundamental problem every single researcher has to deal with. Then, we'll introduce our two main contenders in the statistical ring, the frequentist and the Bayesian methods. We're going to put them head-to-head in the simulation, see how they handle a real-world study, and then, well, we'll try to figure out if there's a final verdict.
Okay, first things first. The researcher's dilemma. You know, scientific research is a really high-stakes game. Every single conclusion, every claim you make is basically like walking a statistical tightrope. You're constantly trying to avoid two huge mistakes.
Just imagine this. You're testing a brand new drug. The early data looks promising. It seems to lower cholesterol. But is that a real biological effect, or is it just random noise? You know, a statistical fluke? Getting this wrong has massive consequences, which is exactly why we need a super rigorous way to make the call.
And that brings us to the two big errors at the heart of this whole thing. A type 1 error is basically a false alarm. You shout from the rooftops that you found something, but whoops, you were wrong. On the other hand, a type 2 error is a misdiscovery. There was something real there, a genuine breakthrough, but your test just didn't see it. So really, all of hypothesis testing is just this constant balancing act between these two risks.
So, let's meet our first contender. For, decades, the undisputed champion in the world of science has been the frequentist approach. This is the gold standard you'll find in pretty much most medical journals and social science papers.
At the very heart of the frequentist method is the famous, or maybe infamous, p-value. Think of it like this. You start by assuming your drug does absolutely nothing. That's your null hypothesis. The p-value then tells you, okay, if the drug does nothing, how weird are these results we just got? If your results are super weird and unlikely, meaning a very small p-value, usually less than 0.05, you get to reject that no effect idea and declare your findings statistically significant.
But there's a challenger rising through the ranks, and it offers a completely different way to think about things, the Bayesian approach. It's getting more and more popular, especially in fields like cognitive science and machine learning.
So instead of a p-value, Bayesians use something called the Bayes factor. And what's so cool about this is how direct it is. The Bayes factor doesn't just ask if your data is surprising. Nope, it directly weighs the evidence. It literally puts your two ideas, the drug works versus the drug does nothing, into a head-to-head match and tells you which one the data supports more and by how much.
And here's a really great way to think about the philosophical difference. The frequentist approach, it's like a courtroom trial. Your no-effect hypothesis is innocent until proven guilty beyond a reasonable doubt. That's your p-value being less than 0.05. The Bayesian approach, though, is much more like a detective's investigation. A detective starts with some initial hunch, a prior belief, and as new evidence rolls in, they constantly update their theory about what's probably true.
Okay, so we've got these two very different philosophies. But how do they actually stack up when it comes to avoiding those two critical errors we talked about? Let's get to the good stuff, a large-scale simulation study that pits them against each other. It's time for the showdown.
And the first major finding from the simulation is all about those false alarms, the type 1 errors. It turns out that when it comes to avoiding claiming a discovery that isn't really there, the Bayesian approach is definitely more conservative. See, frequentist tests are designed to keep that false alarm rate right around their target, which is usually 5%, and they do exactly what they promise. But the Bayesian tests, just by how they work, are more cautious. Their false alarm rate in this simulation was way down, around 2%. They're just much less likely to cry wolf.
But, and this is a big but, that extra caution comes with a price. Being less likely to sound a false alarm means you're actually more likely to make the other mistake, missing a real discovery that's right under your nose.
So when we look at type 2 errors, those missed discoveries, the whole situation flips. The Bayesian tests are more likely to miss a true effect. Now this is really important. This difference is biggest when you're dealing with a small study or when the effect you're hunting for is pretty subtle. The good news is, as you get a bigger and bigger sample size, this gap starts to shrink.
Okay, simulations are great, but let's see how this all plays out with a real-world example. We're going to look at an actual study from cognitive science that tested a pretty wild theory about how our memory works. So the researchers wanted to know, could making horizontal eye movements, literally,
just looking from side to side? Could that actually help people remember a list of words better than just staring at one spot?
All right, first up, the frequentist analysis. The p-value came back higher than 0.05. So, by the book, that means they cannot reject the null hypothesis. But just look at that interpretation. All they can really say is that they lack evidence for an effect. They can't say the effect isn't there. It leaves you in this really unsatisfying statistical limbo.
But now, check out the Bayesian result. They calculated a Bayes factor of about 11.7. So what on earth does that mean? It means the data are about 11.7 times more likely under the null hypothesis, the one that says the eye movements don't help at all.
And this allows the researchers to make a much stronger, much more direct statement. They can actually quantify their evidence and say, hey, we have strong evidence for the null hypothesis. This is something a p-value can never do, and that is a huge practical advantage for the Bayesian approach.
So, where does all this leave us? Is there a clear winner in this statistical showdown? Well, the truth is, it's not that simple. It's not about a knockout punch. It's really about making a strategic choice based on what you're trying to accomplish with your research.
Let's just quickly recap the main points. Frequentist tests, they give you super strict control over those false alarms. You set your risk level at 5%, and that's where it stays. Bayesian tests, on the other hand, are naturally more conservative. You get fewer false alarms, but you run a higher risk of missing a real discovery, especially a small one. Remember, you can shrink that trade-off by getting more data. And maybe the biggest takeaway of all, only Bayesian tests can actually give you evidence for the absence of an effect.
And that leads us to the final, and I think most critical, question that researchers and really the whole scientific community have to wrestle with. As we try to build reliable, reproducible knowledge, what's worse? The false alarm that sends tons of other scientists on a wild goose chase, or the misdiscovery that might just lie buried for years? The answer to that question really does shape the future of science itself.